This is the lecturette for the first part of our solids chapter, where we'll examine the types of solids, that is how they're categorized, as well as look at metallic solids. In these particular two sections, we're going to look at types of solids and categorize them in a couple of different ways. And then we're going to look at the idea of unit cells, that is, the way we describe an extended solid using a small portion of that solid, a small repeatable portion of that solid. And we'll look in particular at cubic unit cells that are seen often with metals. And then we'll look at how we know things we know about solids. How do we know the solid states of compounds when they're in crystalline form? And that's done with an experiment called X-ray diffraction. So first let's talk about types of solids. There are really two different categorizations of how solids can be put into different groups. One is the size of the solid, and the other is what holds them together. And so ionic solids are extended solids. So they're extended, meaning they're essentially a very large structure that goes on and on. This is a small portion of the sodium chloride structure, but it keeps going on in all directions, and we're just showing a small portion of it here. What holds it together are ionic bonds between sodium ions, which are these, and chloride ions, which are these. Molecular solids are held together by intermolecular forces, just IMFs, which are weak. So intermolecular forces are weak, so molecular solids tend to also be very weak solids. They don't have strong structural properties. Network solids, also called extended solids, are also called covalent solids, covalent network solids. Those are held together by covalent bonds, that is, the bonds that hold molecules, atoms together inside molecules. So those are very strong. And things like quartz or diamond are examples of those. The last kind of solid are metallic solids, which are often close packed structures, but not always. But the idea is basically you just have a bunch of metal atoms all packed together like a crate of oranges or a crate of tennis balls. Just essentially a bunch of spheres packed together as close as they can get together. So if we look at this overall table, it kind of puts together the different types of solids as well as their attractive forces, what holds them together, as well as some of their properties like hardness and melting point. So molecular solids are held together only by IMFs, which are weak, and therefore they're soft and brittle, and they also have relatively low melting points for solids, that is. And examples of that would be ice or solid carbon dioxide, which is called dry ice. Ionic solids are held together by ions, so ion-ion forces are held together, and those are strong. So because those are strong, they tend to have high to very high boiling points. They're very hard, but they can be brittle, and the reason they can be brittle is that you can shear across a plane here and move that plane in that direction and that plane in that direction, and so you can cleave ionic solids relatively well, even though they're very hard. Covalent solids are held together, or covalent network solids are held together by covalent bonds, which are also strong. And what happens, they're hard, and they're very hard, they have very high melting points. Metallic solids are held together just by a bunch of metallic atoms, covalently bonding to many metallic atoms around them. And so they have very variable hardness and very variable melting points. So the metal mercury is actually a liquid at room temperature, whereas the metal tungsten has a melting point of over 3,000 degrees. And sodium, for example, has a melting point of around the boiling point of water. So those have a broad range of melting points. So there's a couple more examples just to picture the network solids, because those are the hardest to picture. Diamond is made of a network of carbon atoms, where each carbon atom is bonded to 4 other carbon atoms. And each of those carbon atoms is bonded to 4 other carbon atoms. And so you have this network of carbon atoms where each carbon atom is supporting the position of 4 other carbon atoms, and each of those other carbon atoms is supporting the position of 4 other carbon atoms. And that's what makes diamond so hard. It's the fact that you have all these interlocking pieces where if you move one, you have to move all of them. And the bonds between those interlocking pieces are strong because they're good, strong covalent bonds. Of course, it's similar to this, where instead of just having carbons bonded to carbons, you have a silicon Well, look at this piece right here. You have a silicon bonded to an oxygen bonded to a silicon. And those silicon-oxygen bonds are also very strong. So whenever you have covalent network solids, they tend to be very strong solids. Now we're going to look at unit cell types and give the idea of unit cells. And we're going to first preview different unit cell types and then go over what a unit cell actually is. Unit cell types can be different ways we describe a solid state structure, which is very large, using the smallest repeatable portion of that. And so here's a unit cell called a simple cubic unit cell, meaning that we have essentially just 8 atoms in a cube, where you have 90-degree angles between each of those sets of atoms. So each of those are right angles. And so what we do is we think about this cubic unit cell as the smallest portion of an array of atoms that would just be lots of atoms in line on the x, y, and z axes. A body-centered cubic unit cell is that same structure, but with another atom inserted in the middle. And a face-centered cubic unit cells, you have that cube, but there are extra atoms inserted on the faces between, essentially, that sets of things. So those are 3 different kinds of very common unit cell types. So what a unit cell is actually is it's the repeating unit for a solid, where if you go and repeat that unit in any direction and adjoin unit cell edges, you get the same structure. So here's just a pattern. We'll do this in a 2-dimensional version. If I do, I'm going to change my color here to yellow. If I do that square there and say that's my unit cell type, what would happen is when I draw the next square over right here, that would also need to be the same, and it's not, so that's not the unit cell. I could, on the other hand, draw, let me erase that too. I could also draw, say, this here. Now, if I take that square and move it over, I get this next square over, and that is a good repeat of that. And if I go downward, I'll get the same thing over again. So that is a good repeating unit. But the question is it the smallest repeating unit? So to be a unit cell, it has to be the smallest repeating unit. And let's say you don't actually have to be on the atom. Let's say we go from here to here to here to here. Is that a repeating unit? If I move this over to here, it's not the same, because now the light-colored part is on the left, whereas it was on the right. So this might well be our smallest unit cell. Let's see. I think that's it. I think that is the smallest unit cell there. Okay. Here's one you could do in class, but think about where you would draw your edges for making these the unit cell of choice. Another example here, where the unit cell here, where it clearly would be there. That's not a unit cell. What you need to do is you need to figure out a place where you could, in fact, go. So that is a good repeat unit. So if you go to either left, right, up, down, side, you get the same thing. But you can, I think, do half of that. I think you go from here to here to here to here to here. And I believe that's also a repeat unit. If you go up, down, left, or right, it just continues in the same shape. So because this is smaller and that is larger, this is the unit cell, because it's the smallest repeat unit. This is a repeat unit, but it's not the unit cell. All right, now let's return to our unit cell types. When you're talking about a unit cell, what you need to do is we need to kind of decide how many atoms that unit cell contains. And so if we look at our primitive cubic unit cell, we just have 4 cubes. If we're going to be having essentially a set of these together, what's happening is that, change that color back. Looking at this 2-dimensionally, looking at essentially a face of this. If our unit cell contains those atoms, those atoms, those atoms, those atoms, essentially those 4 atoms, the next unit cell would be the next piece over. But the repeat unit doesn't go from edge of the atom to edge of the atom. It goes from the centers of the atoms. So that's one unit cell. That's the next unit cell. So blowing that up a bit, what's happening is we're going from there to there to there to there, and there to there to there. So what we really want to know is what's inside that box, what's inside that unit cell. And what's inside that unit cell isn't this entire atom, it's only the portion of this atom that's inside the box. And so what we do is we take our unit cell and we essentially shear the atoms, cut the atoms, so we see which atoms are inside and which atoms are outside. So if we did this, our unit cell would be here. And so this part of the atom out here is not inside that unit cell, but this part is. And so how much of that atom is inside the unit cell depends on the position of that atom. And the idea is that if you have an atom that's on the face of a unit cell, it's shared half in one side and half on the other side. If it's on a corner of the unit cell, it's shared 1/4 in each of these 4 boxes. So something that's on an edge will be counted as a quarter inside. Something that's on a face, let's say this one here, is a half inside. Something that's on a corner, an actual corner, is actually shared between 8 different unit cells. So that's only 1/8 inside the unit cell. So depending on the position of an atom inside or on the outside of the unit cell, the way you count the atoms for that unit cell is if it's inside, it counts fully. If it's on the face of the unit cell, it's a half. If it's on the edge of the unit cell, that is like in this position here, that's a quarter. If it's on the corner of the unit cell up here, it counts as an eighth. Only 1/8 is inside that unit cell. And we need to know this because we often need to know how many atoms are actually inside the unit cell. So let's look at an example here. So for this one here, let's say that this is, I'm colorblind, let's say this is red and that's green. What we have is we have one red atom inside, and that counts as 1, so there's 1 red atom. We have 8 green atoms, and they're on the corner, so they count 1/8 each. So there's actually a total of 1 green atom. So even though the unit cell shows 8 green atoms and only 1 red atom, this unit cell actually has the inside of the unit cell actually has 1 green atom for every 1 red atom. This one here is a lot more hard. Let's say we have gray, and let's say we have green. For the gray ones, we have 8 corner atoms. That's this one, 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 and the one in the back. And now those count as an eighth each, so that's 1. Plus the gray ones also, there's 1, 2, 3, 4, 5, and 1 in the back. 6 on the faces, and those count for a half each, so that's another 3. So we have a total of 4 gray atoms. Now if we look at the green ones, it's a little hard to tell. One of the talents you have to get better at is kind of looking at these pictures three-dimensionally. If you look at the way the bonds go, these green ones are inside, and so there's 4 of them here, 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 and here, and there's 4 of them here, 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 and here. And so that's a total of 8 green atoms times 1, because there's 1 green atom for each, there's 1 green atom for each, 1 green atom inside for every atom because they're all inside, so that equals 8 green atoms. And so this particular unit cell has 4 gray atoms and 8 green atoms. This unit cell has 1 green atom and 1 red atom. Okay. Now, let's go ahead and do some things with these. What percentage of a cubic unit cell, that is an atom on each corner, nothing else going on, is actually inside the unit cell, inside that box? What we do is we call the unit cell edge length 2r, where r is the radius of the atom. And so what we have is we have this box, not just a box, it's a cube, where the edge length is 2r. And then what we do is we have a total of, remember we have 8 atoms in corner positions, times 1/8. 1/8 of each of these atoms is actually inside that box, and 7/8 is outside. So it's 1 total atom inside the unit cell. The percentage of the cubic unit cell that's filled with the atoms is the volume of the atoms inside divided by the volume of the unit cell times 100, of course, to get to the percentage. The volume of the unit cell is equal to 2r cubed. That is, it's the edge length cubed. That's the volume of the unit cell. So that's 8r cubed. Because you have to, oops, sorry, that's a cube there. Because you have to cube the 2 and the r. The volume of the atoms inside the unit cell is 1 atom times the volume of an atom, and the volume of a sphere is 3/4 pi r cubed. So that then becomes 3/4 times pi, so 1.333 times 3.1415. So that comes out to 4.189 r cubed. So the percentage then is that times that fraction times 100. So that comes out to 52.4%. So of this cubic unit cell, only 54% is actually, only 52% is actually filled up with atoms, and the other 48 roughly percent is empty space. And the empty space is essentially the space that's the gaps between the atoms. Okay, let's look at another example. Let's look now at a body-centered cubic unit cell. And here, the edge of the unit cell can't be related to R directly because there's a gap there. So you don't know what that edge length is exactly from the connection of the atoms. But what does happen is there's let's go for the yellow. There is a line from here through the center atom to the back atom. So you can see it's kind of going behind that atom there, through the center atom. And so that atom is going across the body unit cell from front left. Nope, go forward. Okay, from front left through the unit cell to the back right. And that diagonal is actually using atoms that are touching. So you have one atom here, so that's R. You have the atom in the middle, so that's 2R, because it's the diameter. You have that atom there, so that's an R. So that diagonal is 4R. So 4R equals the diagonal. And that diagonal is equal to the square root of 3 times the edge length. Now, what happens is, what we're asked here is we have a body-centered unit cell, and the unit cell edge length is 343 picometers. What's the radius of the uranium atom? Well, what we know is that the edge length is the square root of 3 times the edge length equals 4R, which is what we're looking for. Is we're looking for the radius of the uranium atom, which is 4, which is R. And so we'll take square root of 3 times the edge length, 343 picometers, divided by 4. And when we do that out, we come up with 149 picometers. And so this worked because the key here is the connection between the edge length and the diameter, the diagonal of across the unit cell from here over to there is equal to the 4R, because those atoms are touching from here to here to here. Okay, so now let's look at a different kind of unit cell type. So we've looked at simple cubic and we've looked at body-centered cubic. Now let's look at face-centered cubic. And face-centered cubic unit cell is an example of what's called cubic closest packed structures, which is essentially the kind of packing you get if you take a bunch of spheres, pack them together as best you can, the most efficient packing you can get. And what that really amounts to is laying down a layer of spheres, then laying down another layer of spheres on top. And the spheres don't kind of line up with each other directly. What they do is they go in the gaps, because they can fit down lower in the gaps. And so you can get one layer and then another layer that's kind of offset by 30 degrees or 60 degrees? 30 degrees. And then a third layer on top. And it turns out that there are two different ways this can happen. You can have every other layer aligned directly with the layer 2 layers above it or below it. Or you can have every third layer. So this is here, this is here, this is here. Essentially it keeps twisting around to the left or the right, depending on what you're doing. But then the fourth layer would be there. So this packing would be CBA, CBA, whereas this layer would be AB, AB, where the A's, B's, and C's are representing essentially the twisting of the layers. So that means that here's 3 layers repeating over and over, and here's 2 layers repeating over and over. Well, it turns out that this particular version of close packing is the same unit structure as the face-centered cubic one. And it doesn't really look it. But what you do is you take this closest pack structure and you actually twist it. You take the whole structure and rotate it. And it turns out when you rotate it, you end up with this structure here. Like the body-centered cubic unit cell, there is a relationship for the face-centered cubic unit cell with the volume of the unit cell, the edge length, and the radius of the atoms. And so what happens here is if you take that is the face of the unit cell, and the atoms along the face are touching, and so the diagonal there is equal to 4r, because you have those atoms touching there, and therefore 4r is going to equal the square root of 2 times the edge length. So that's the edge length there. So that edge length is equal to square root of 2 times that edge length gives you 4r. And you can use that in relating the structure to other things. So let's look at an example of this. A face-centered cubic unit cell has a density of 1.54 grams per, calcium metal has a density of 1.54 grams per centimeter cubed. It has a face-centered cubic unit cell, and we want to know what's the radius of a calcium atom from that. Well, here's the plan. This is a pretty tall order to do, but the way we do it is, what we know is that we can add up how many atoms are inside that unit cell. And so what we can do, let's do this first. Let's add up how many atoms are in a unit cell. So we'll do number of atoms, and that will give us number of moles of calcium. Number of atoms of calcium, number of moles of calcium. Number of moles of calcium will give us grams of calcium. If we know the grams of calcium, we can determine the volume of the unit cell. And the reason we can do that is we know the density. If we know the volume of the unit cell, we can determine the edge length. If we can determine the edge length, we can determine 4r. If we determine 4r, we can determine r. So it's a lengthy calculation, but not as bad as one might think. So first let's figure out how many atoms are in the unit cell. What we have is in our unit cell, we have we have 8 atoms on the corners. So there's 8 corner atoms. And those get multiplied by an eighth because each of those corner atoms is only 1/8 inside the unit cell. So that's 1 calcium atom. Then we have 6 atoms on the faces. So it's 6 face atoms. And each of those is 1/2 inside the unit cell. So that's another 3 calcium atoms. So that gives us a total of 4 calcium atoms. Okay, so we have 4 calcium atoms times 1 mole of calcium times 6.022 times 10 to the 23rd calcium atoms. So that gives us moles of calcium. And then we can use our periodic table and relate moles to grams. The molar mass for calcium is 40.08. 40.08 grams per mole of calcium. So we're now at grams, and now we want to convert grams to centimeters cubed. And so we know the density, and so what we do is we have grams, so we're going to use 1 centimeter cubed divided by 1.54 grams. So let's do all that out. So that comes out to 1.7287 times 10 to the minus 22, and our units are, everything cancels except centimeters cubed. Centimeters cubed. That means the edge length for a unit cell, that's the volume of the unit cell, the edge length is equal to the cube root of that. So the cube root of 1.7287 times 10 to the minus 22 centimeters cubed. So that comes out to 5.57 times 10 to the minus 8 centimeters. So that's the edge length. 4r, 4 times the radius, is equal to the edge length times the square root of 2. So therefore 4r is equal to, we'll just take our number and multiply it by the square root of 2. 7.878 times 10 to the minus 8th centimeters. And therefore, the radius is equal to that divided by 4, which is 1.97 times 10 to the minus 8th centimeters, which is 197 picometers. Okay, so that was a very involved problem for getting from experimental information, that is the type of unit cell and the density of a metal, both measurable properties, to figure out an atomic scale property, the radius of that atom. Okay, so we did what fraction of a unit cell, a simple unit cell, is filled with atoms before for a simple cubic unit cell. I believe it was 52.4%. Let's do that same calculation for a face-centered cubic unit cell. Here what we have is we have a unit cell where we contain a total of 4 atoms. And the volume of the atoms in the unit cell, therefore, is equal to 4 times 4/3 pi r cubed. So that's going to be 16 divided by 3 equals that, times 3.1415. So that comes out to 16.75 r cubed. That's the volume of the atoms inside the unit cell. Recall that the edge length is equal to 4r divided by the square root of 2. So therefore what we do is we're going to use that value cubed. So it's 4r divided by the square root of 2 cubed. And so that's going to come out to be 22.63 r cubed. So the percent filled is equal to 16.75 divided by 22.63. The r cubes will cancel, times 100. It comes out to 74%. 74.0%. Notice that this is much higher than we had there. It is what you expect because the face-centered cubic unit cell is what's called closest packing. So the greatest volume of the unit cell should be filled. And so here's a summary of that. This is the one we just did. That's what we did before. If you do the same thing for a body-centered cubic unit cell, it's mostly filled, but not so much as the face-centered closest packing one. All right. The last thing we're going to do is we're going to look at how we know unit cell dimensions experimentally. The way we know them experimentally is by doing what's called X-ray diffraction. It's an experiment where you shine X-rays on a crystal, and they will diffract, and you will see diffraction patterns associated with the lengths, the distance between planes of atoms. So we have a plane of atoms here. We have a plane of atoms here. That distance there, d, can be seen in this experiment. And the idea is that that distance, d, will correspond to the wavelength of light that's incoming. That's the wavelength of light you're shining on the crystal. Some integer called n, which is called the order of diffraction. And so what will happen is you'll get a signal for n equals 1, n equals 2, n equals 3. And what you can do then, and also the angle at which you're shining the light in. So you know this angle you're shining in because you see the crystal and you're shining the light on it. And so basically what you do is you use laser light, which has a specific wavelength. You shine light at a specific angle, or you actually kind of change the angle and see where you get these signals, and then you can calculate d from that. And so let's look at an example here. Silver metal crystallizes in a face-centered cubic lattice, and we use X-ray radiation from a copper target. What that means is that's the thing you're using to make the X-rays. Copper has nothing to do with the experiment other than it's the thing that you're using as the X-ray source. And the X-rays have a wavelength of 154 picometers. So that 154 picometers is lambda. Then what we do is we are looking at a silver crystal. That's the thing we know has a face-centered cubic lattice. And we see that we get a signal when theta, the angle, is 22.18 degrees. And the first thing we're going to do is we're going to look for the D spacing. That is the spacing between the rows of atoms. And we're going to be assuming that that D spacing is equal to the edge length. So that's D. So what we do is we are going to solve this. The one thing we haven't mentioned yet is n, the order of diffraction. And that's the second order diffraction there. And that's something you see during the experiment. That's something you can't just calculate. It's an experimentally observed phenomenon. So D is going to equal 2 times theta divided by 2, so the 2's are going to cancel, divided by the sine of, 2 times lambda, divided by 2 times sine theta. So the 2's will cancel, so we have our lambda value of 154 picometers, divided by the sine of 22.18 degrees. And so when we do that, let's see. So we'll take 154 divided by sine 22.18. That comes out to 408. And though the units there are picometers. So that's our edge length, 408 picometers. And the next thing we want to do is we want to talk about what's the metallic radius of a silver atom. And the relationship between, for face-centered cubic unit cell, is that the edge length times the square root of 2 is equal to 4 times the radius. So we can solve for the edge, we now know the edge length, so R is going to equal the square root of 2 times the edge length, 408 picometers, divided by 4. And that comes out to be 144 picometers. So that's then the radius of the silver atom. And that ends this lecture.